Hello. In the last video we completed this table, but ultimately what we're interested in is what does the graph of quadratic relationships look like, and how can we figure out shortcuts to graph these without actually filling in a long table of values. So what we're going to do in this next video is we're actually going to graph these. Now, we've already discussed the idea that we're building off of this relationship y equals x squared. What we call this the parent relationship. The parent relationship or sometimes we say the parent graph, or sometimes we say the parent function. Basically what this means is the parent relationship is the relationship that we start from, that we initially start from when we go through and do our graphing. So the first thing I do is I'm going to graph y equals x squared, and it's really helpful here if you color code your response. So that graph is going to be green. So if I come up here, I can read it off this table of values. So this is my x, y, x, y, x, y. So we know 0, 0. Let's see if we can scroll this up. There we go. We know -3, 9. It's going to be here. We know -2, 4, 1. So now I'm going to give this a nice smooth curve. It kind of comes down like this. And we're going to do the other side, 1, 1, 2, 4, 3, 9. You want to get to the point where this just becomes second nature, this parent graph. And so a couple of things we want to make sure we remind ourselves of. We put arrows on the end because this continues on forever. This shape is called a parabola. We want to be able to identify a couple things. We want to be able to identify the vertex. Right? So the vertex is always a point. So the vertex is where we change direction. So that would be here, 0, 0. We want to be able to talk about the axis of symmetry. So the axis of symmetry is always the line, and it's the line that where we get a perfect reflection across. And we see here is the line cuts right down through like this. So there's my axis of symmetry. So my axis of symmetry, remember, very important, is always the equation of a line. So this is going to be x equals 0. And we want to know the direction of opening. And the direction of opening is going to be up because this parabola opens upwards. So now let's do the other graphs. So if we take y equals 3x squared. So a couple ways I could do this. Of course, I could read this off the chart. So let's start at x equals 0. So we see, again, we have the point 0, 0. And then I have the point 1, 3. And then I have the point 2, 12, which is going to be up here. And I have the point 3, 27, but that's going to be right off the graph, so I'm not going to include that. Now, of course, I need to do the left-hand side, and so I could do -3, -2, -1. But let's make sure we understand how we can use this axis of symmetry to our benefit. So what happens is, notice, this axis of symmetry means that on the other side it's going to look exactly the same. So if I take one step to go from there to there, I'm going to take one step out to here, and there's my other point. -1, 3. If I take 2 steps to get to the axis of symmetry, I'm going to take 2 steps to come over here. So I'm going to get -2, 12. And I want to get this nice shape here. There we go. And of course, the minute I graph this, I want to start thinking about the various features of this graph. So I want to ask myself, what is the vertex here? Well, the vertex is 0, 0. Remember, the vertex is always a point. Axis of symmetry, we can notate this AOS. Again, the axis of symmetry is always the equation of a line, so it's x equals 0. You can see it has the same axis of symmetry, and I want the direction of opening. Direction of opening. We go DOO for short, and the direction of opening is up. Okay? Just put direction of opening. There we go, just short form it. So again, really important point is that we can actually take this and substitute in a table of values and figure out the curve. But the whole purpose of what we're doing here is we want to understand a topic eventually called transformations. So we want to look at how can we start from our parent relationship and end up at our child graph. So the question is, well, what do I do to go from the green curve, which is y equals x squared, to the blue curve, which is y equals 3x squared? And what we noticed is that we took each of the y values and multiplied it by 3. 9 times 3 is 27. 4 times 3 is 12, 1 times 3 is 3, 0 times 3 is 0, and then continue on. So if we know what our parent graph looks like, we can actually do this relatively quickly without actually including a table of values. So if I sketch my parent graph here, I can take each of these points and just apply whatever the multiplication is here. So I'm going to take, let's do this next one, y equals 1/4 x squared. So we see the parent relationship, or parent graph, is y equals x squared, which is right there. So we're going to take the y value and multiply by 1/4. So 0 times 1/4 is 0. 1 times 1/4, it's going to be 1/4, so it's going to be somewhere about there. I'm going to approximate. Oh, pardon me. 4 times 1/4 is going to be 1. 9 times 1/4 is going to be 9/4. And 9/4 is 2 1/4, which is going to be about here. And now this is where I have to be careful when I'm graphing this. These other two examples just continue straight up. However, the y equals 1/4 x squared is actually going to have some more points, integer points, on this graph. So what I'm going to do is I'm going to have to do a little bit of rough work here. So I'm going to say, well, we know that 4 squared is equal to 16. So we're going to take 16 divided by 4 to give me 4. We know that 5 squared is equal to 25. So what I'm doing is I'm calculating the x squared value. So then we get 25/4. And now, again, a way to visualize this is write it as a mixed number. So we're going to get 6 1/4. So we're going to 5, 6 1/4. Just about there. Again, we're writing, this is in the spirit of graph. It doesn't have to be exact. Let's do one more. 6 squared is 36. So 36/4 is going to give me 9. So then this is what this side is going to look like. So again, I could go through and I could calculate each of these points by applying taking the y value on my parent, which is the green, doing this. Then we see 4 times 1/4, 1. 9 times 1/4, this value. And again, due to the nice symmetrical nature of these graphs, I can just count across. So if this is 5 across, 5 across, 6 across, 6 across, and there's my second curve. Okay. All right, let's do this last curve now. Let's do this one in pink. So this one can throw students off a little bit because there's a negative here. Well, not to worry. It just means that instead of multiplying the y value by 2, I multiply it by -2. And if you watched our earlier video, you'll recognize that if I have a negative in front of the x squared, that means that it's going to change the direction of opening. So we know, actually before we go on, let's just write our information down for the black curve, the y equals 1/4, the vertex is 0, 0. The axis of symmetry is x equals 0, and the direction of opening. Pardon me, just make pause this for a second. That was just my oven going off. I'm cooking some beets. Direction of opening is up. Okay. So again, I was going to say the last one, we're going to make that pink. So I'm going to go totally off my parent graph, which is y equals x squared. So I'm going to take each of the y values and multiply them by -2. So 0 at x equals 0, y is 0. So times -2 is still 0. If I have x equals, we have 0.11, so at 1 we're going to multiply y as 1 by -2, so that's going to go to 2 and then down to -2. And then we have the point here, and maybe this will help in terms of visualization. This is the point 2, 4. So let's go back to pink here. So I'm going to leave 2 the same, but 4 I'm going to multiply by -2. So that's going to become, oh, it goes right off the graph, so it's down here somewhere. So then the question is, do I need to do this one? And the answer is no, because it's actually way off the graph. So now I'm just going to give a nice smooth curve. Here we go. And then I can do it either off the other points on the graph, or I can use a symmetrical argument here just by counting across. And there we go. So there's that last one. So for this guy, the vertex is at 0, 0. The axis of symmetry is x equals, and the direction of opening is down. And the reason why it's down, and this is a very important observation to make here, is that since coefficient is negative, okay? Of course, if you need to get some of these other points here, specifically this would be useful in the y equals 1/4 x squared cases, you can always substitute values and test a few. But what we want to head towards is eventually moving away from actually using a table of values and starting to recognize these, what we call transformations that are being applied to our parent graph. So we always want to have our parent graph and think of what the child graph or the resulting graph looks like relative to that. Initially, we're going to do a number of detailed graphs, but over time, what we want to start to recognize is it's not the fine details that are important, but the general, what I call the spirit of the graph. How does it look relative to other graphs that we have? Specifically, in our case, our parent graph. Last point. I know this question didn't ask for vertex, axis of symmetry, or direction of opening, but that's something you want to make almost a reflex. Every time you graph a parabola or a quadratic relationship, we want to say to ourselves, what's the vertex, what's the axis of opening, and what's the axis of symmetry, and what's the direction of opening. Doing this is not only going to help you in your graphing, but also specifically in word problems, because these values carry specific weight when we're dealing with word problems. I hope this helped.